not gonna go.
Look at what you've done.
He put me in a D because this was earlier.
Did you get like 20?
I can't stand it.
Yeah, I got point
But,
eight.
no, he gave me 6.
The last time I checked, the last time I checked
I
my
want you to
grades,
look me in the eye.
last time I,
Oh, that was
last time
so
I checked
much
my grades
more
California, it
This
was
was supposed to
70
be.
point.
This is what I
Because if
did.
you can't do that, you're not man.
It was like a 70.3,
I turned
and I
that
didn't see any
whole,
grades for like a month and a half.
whatever
And
into
then it was
the-
B. I'm like, I
Dude,
swear, I'm doing
something
anything.
else, you never turn in anything on
I'll
time.
bet my next show.
Is there anything that you were supposed to?
Everyone was freaking me out by Cap 2. Cap 2 is the easiest Cap 2 is for me to take.
No, that was hard because
this is supposed to be.
she didn't make any sense.
Is that correct?
Is
Is it correct number?
No.
Because this was, this acceleration was.
And he
Oh,
said,
yeah.
oh,
Or just the things spinning around the table.
Okay.
I can't understand.
You showed them something.
And then it jumps straight. Okay.
No, it's like Chinese English.
Well, his isn't right, but his process is right. I think.
Yes, Danilo says
I didn't get that.
theta instead of theta.
I don't think you said that. Did you say this?
Yeah.
And find, this is a passage, hey, you find your ass.
Yeah, it's supposed to be
Find your ass and toes. And so I was like,
Hey, but you
find your
remembered
ass
it.
and toes.
But what I had in
That's a living. I've heard it pronounced salon.
I don't know what was wrong with my method. It might have just been because there's so much.
You call it ass and toes.
I had this whole freak out of this.
I can't.
What'd you get? Well, you're just like,
I got like one. People got English barriers. I like, what's that? The whole time. That was the thing. So. He was pretty good with that.
I don't have a problem with this, except there was
We'll add the coefficient after we do this.
All right, so let's take a look.
If you want transfer, you have control.
Apparently, I had the order of your book a little bit off. Gravitation stuff is chapter 7. This is part of chapter 6, so we're sort of dropping back. Some textbooks put all the circular stuff in one chapter, so the gravitation goes in with centripetal force, and I just lost track of this book. So what's happening in the overhead view, we have a circular track of radius r. A car is going around it. The road is banked, or the track is banked. So when the car is over here, we can look at it from the point of view of there's some angle theta here. So this is a rear view. It is frictionless. And the question is, how fast does this vehicle need to go in order to be able to go around the track without sliding to the top or the bottom? So we start on like half the other problems we've done. Pardon?
by doing things.
By doing things, yes.
Fourth diagram.
Force diagram, yes.
Now we have it, yeah.
All right, so basically it's car on ramp, well, basically right there. So I draw I have my car, I have my ramp. And F-tong.
Well, you got the weight pushing down. The car going down, the weight from the car.
I'm nitpicking the language.
You have the gravitational force pulling down on the car.
Yeah.
I was pointing down the car.
Yeah, you said pushing down. And,
Yeah.
and the reason why conceptually they are being pulled together
Yeah,
and they're
it
not
makes sense.
being pushed together. There's not some gravitational force is not like a giant hug.
Yeah, it made it
pushing.
sound like something was sitting on top of it.
There's also normal force diagram.
Yeah, 45 now.
Yeah, so the normal force is perpendicular to the surface right here. This is the exact same force diagram as box on ramp if the ramp were frictionless.
There's no friction.
So the car
there's
is
no
sideways, right?
Well, I'm just saying for the purpose of that.
The car's sitting sideways, right? Because it's a race track, right?
Right.
Like that.
Yes. All right, so after we've done the force diagram, what next?
Oh, yeah, we have our, what's the other acronym? Something else.
Put your,
Facades.
Facades. All my emotions. Facades.
Oh.
What's next?
Hold on.
Sums of forces equations? Yeah.
Not yet. The equation comes in a while. What?
Acceleration.
don't you have
Before
friction?
that,
Acceleration.
acceleration.
Don't you got friction?
direction.
Because the car is racing around, you can have it on that right side front tire real hard.
That's a frictionless surface.
Oh, okay, sorry.
Yeah, that's what this is representing.
Okay.
We're gonna add friction later.
No.
We'll bring reality in.
You don't have
Let's
to.
do this first.
It's okay, you don't have to. Leave it out.
All right, so we have no friction, so there's no friction, there's no string, there's no other, just car, and it's just going around in a circle, and we dealt with those two.
Direction of acceleration.
What is the direction of acceleration? And this is critical to the rest of the problem.
Towards the
Constantly changing?
Towards the center of the.
Pardon?
Constantly changing.
We can generalize it though.
Towards the center of the circle. Ooh.
When the car is here, what's the direction of acceleration?
Towards the center.
Which way is the center?
Left.
Yes.
Oh,
The acceleration is that way. The biggest mistake students make is they put the acceleration that way. That is a box sitting on a ramp. That's the direction of the acceleration it would go. In
What's your
this
definition?
context, if that's the direction of acceleration, you're saying that the car is doing a loop like this.
You saying they put it straight, like,
No, they
The
put
line
it.
straight
they
off the
put
car?
it.
The mistake is to have acceleration down the ramp.
oh,
The
okay.
acceleration is not. The acceleration is to the left.
Oh, okay, I see what you're saying.
It is traveling in a horizontal circle. So therefore, we now do the coordinate axes. I would recommend one of the axes to be in the direction of acceleration.
Oh, weight. That's very sad. Weight and acceleration. Direction, weight, direction, acceleration. That's perpendicular to each other.
All right, so I had, which way J hat?
So, up.
Okay. It could have been down, but up, I heard first, that works.
Which is easy. We'll
Sometimes.
just do it in the opposite direction of I.
So, again, we're doing facades. We did the force diagram, acceleration, coordinate axes. D.
You would have to,
Oh, yeah.
the normal force,
That's a dismantle.
Yeah, we do something with the normal force.
you have to decompose it.
Yes.
So we decompose decompose it. So we need to figure out how much of the normal force is to the left and how much is up. Now, I can go through the geometry, especially with this group. I'm gonna do it a slightly different way to start with. We'll get to the geometry, but when I draw my angles, they almost always look like they're about 45 degrees. And so I'm gonna draw it differently. I'm gonna draw this slope, except I'm gonna make it a small one. So if it is small, if that is my angle theta there, my normal force is perpendicular to that. And I'm trying to figure out how much of it is to the left and how much is up. I have two non-right angles here. I have this angle here and this angle right here. One of them is smaller than the other. Which one of these is theta?
The smaller
Which is,
angle between the ramp and the.
That'd be the angle that
acceleration.
controls the.
between the ramp and,
Well-
that one's the smaller angle?
No, the top one.
That one's the smaller angle. Yeah, there's theta right there.
Is that, what is that theta thing that you, is that the top of the car? Where is that on
Theta.
the thing?
Where is this?
No, the thing with the angle, the triangle with the theta. That
That-
thing, where's that relation to that?
Oh, that's this angle right here. That's the banking of the
Oh, that's the
road.
bottom. Okay, that's the curve. Okay, I see what you're talking about. The bank, flat.
Yes.
That's the bank, yeah. That's
Yes.
what you're talking about. And that thing you just drew looks like up top and there, 90-degree angle and the theta that you're pointing out right there. What's that again?
I was just showing, because in order to break the normal force up, one of them is going to be y sine theta, and one's going to be y cosine theta.
Okay.
And I was just showing a different way of figuring out which one is going to be which.
Okay.
So if I can identify this right triangle right here, I can identify which one's theta. then, well, this is the adjacent side, so this will be y cosine theta.
Yeah, I'm just wondering what that right triangle came from again, though.
This right triangle?
Yeah.
Whenever I'm breaking things up into components, I'm breaking them up into components that are perpendicular or parallel to these things.
Okay,
How far over, how far up?
okay.
Since that's at a right angle, that's where it's coming from. Normally, I draw my vector like that, and I break it up into components like this.
Yeah.
I just made this a smaller theta down here, so a much steeper value for normal force this way.
Okay, I see, it's a line for the Y. Okay,
Yeah, that is my normal force right there.
okay, I see what you're doing.
Okay. Other questions? All right, so method number one is to come up with a scheme to try to draw it at least more realistically. If you are still flummoxed, because who knows the way your mind's working on a day of a test, I have a skinny triangle right here. I know sine and cosine, one is going to be bigger than the other. If I draw it even remotely correctly, whichever one between sine and cosine, this is going to be the smaller of the two. Now, since if theta is less than 45 degrees, this will be the sine, and this will be the cosine. Or we could just go the straight geometry route. We don't have to worry about drawing it skinny. I've got this right here. This is my angle theta. My normal force is perpendicular. I'm breaking this up into components. As we'll extend it. We're just doing geometry here. This is a right triangle here. That is a right angle there. If this is theta, this is the complement of theta, because that's a 90-degree angle there. Now looking at this triangle,
Which means the top one is theta.
that has to be theta. Whichever way you want to look at it. We end up with, we have our car here, we have weight acting down, we have the normal force times the cosine of times the sine of theta towards the center of the ramp, and y times the cosine of theta up. That is the force diagram from which we can do the equations of motion. So now, what are our equations of motion? When doing equations of motions, what is the template?
I mean, force equals mass times acceleration. Net force equals mass times acceleration.
Okay, so that's our starting point. How many equations of motion will we have?
1, 2, well, I and J.
Yeah, that's two.
Okay.
So, what is the I equation or the J equation? Give me one of them.
The Y.
Y minus W.
All right. So y minus w.
Negative omega cosine.
What?
Are we going based on forces acting on the diagram?
Oh, I mean,
That's inserted?
We're
Oh, right
here.
there.
We're here.
So that's negative y sine theta for I hat.
No, it's y sine
You
theta
have for
because.
J hat.
Y sine theta.
Y cosine.
Ah, not J hat either.
And then y cosine, well, yeah, sorry.
For
Y
J hat.
cosine theta minus w,
Yeah.
isn't that?
0.
And the other one's equal to NA.
Centripetal.
Ah. Yes. Do we need to put the centripetal there, or?
No, and you don't need to in terms of if this were a test or quiz, just so long as you recognize that it is. I'm putting it there to emphasize this is centripetal acceleration, and this,
Now, why is
recognizing that is important for the next phase. Yes.
Now, why is it Y sine theta equals MA? Where'd that come from?
So for the I hat, I have only one force in the I hat direction.
Yeah.
And so that's F equals M, and so that's the only force in the I hat direction.
Oh, okay.
Acceleration we established is already in the I direction.
Yeah.
So F equals ma.
Yeah, the mass times acceleration.
And here it's also mass times acceleration, but there's no acceleration vertically, so this acceleration is 0.
Okay. So it's always MA. It's always MA, then it equals.
F is, yes, always ma.
Okay. So that's always force.
Until someone shows that Newton's second law is complete.
Okay, that's, okay, so it's always force, then it equals the force, okay, I see.
Yeah, so it's all,
I forgot.
force is in the positive direction, is equal to mass times acceleration in that direction.
Yeah.
And then force up minus the force down, because we said up is positive, is equal to mass times the acceleration in that direction, which is 0. Other questions right now? All right, so substitution. For what do we have an independent formula that does not depend upon this situation?
Centripetal acceleration.
All right, we have a formula for centripetal acceleration. What else do we have a formula for?
Weight.
Yep. So it becomes y sine theta is equal to, what is the formula for centripetal acceleration?
V squared over R.
Or
Omega squared R.
why use v squared over r instead of omega squared r?
What we're asking. Look.
And then we have y cosine theta is equal to mg. 2 steps in 1, brought the weight over and did the substitution. I'm solving for v, but I have 2 unknowns here. V is an unknown and y is an unknown. So I need to get rid of the y's.
Solve. One for y, one for the other.
So cosine inverse of mg equals y.
All right,
Divide.
inverse of cosine. Reciprocal of cosine. Yeah, be careful, this is one of the reasons why I really don't like the inverse as why I prefer arc instead of inverses, because of confusion there. We can cut out a step here if we just divide the left sides and divide the right sides. We can divide both sides by things that are equal and we're good. This way the y's cancel out immediately. And we're left with tangent of theta equals, well, the masses cancel out over here, v squared over gr. V squared equals gr tan theta. Mathematically, v would be equal to plus or minus the square root. However, physics has boundary conditions and negative speed doesn't make any sense by what the definition of speed is. So now we can turn it into a light jug problem. So let's say theta is 30 degrees. Let's put this on Earth. And the radius, I guess I switched from a capital R to a lowercase r, so why don't we just make them equal to each other? 100 meters. So the radius of curvature is a little bit bigger than a football field. Or actually end of end zone to end of end zone, it might be about right. So the speed, that optimum speed, in order to be able to take this curve, is the square root of 9.8 times 100 times the tangent of 30 degrees. $23 point something?
77 meters per second.
Roughly, what is that in miles per hour?
53.
Probably a little bit less than that, but probably just shy of 50 miles per hour.
Really?
Double it and add a little bit.
That's what I pretty much tried to do.
You said miles per hour?
Yeah.
Quick question,
About 53.
when we're doing this, now this is
It's
completely off
53.2?
topic.
I apologize, you were You were right.
It was 53?
It was 53.
Oh, pretty good. But anyways, as far as this goes, why don't we, I know it's for physics sake, but why don't we just use inches, feet, miles per hour, and all the American units? Because I know it's that, but that way, when we're calculating the problem, we have more of a roughly idea if we're accurate or not. Just wondering, because it's just the units. Answer would be the same, it's gonna be units.
Part of it is, it's a physics thing and just the global standardization. Physics is not a national thing, but it's a world thing.
Yeah.
And so,
Because you can always convert, that's what I was just wondering, but.
yeah, you could always convert.
Yeah.
Ultimately, it really depends on what you're doing. I mean,
Yeah.
most people in here usually want to be engineers of some sort.
Yeah.
And so if you're working for an international firm, then you're gonna have to be able to deal with this.
Yeah.
If you're gonna be working with American
American,
companies only,
yeah.
then you probably can get away with just doing feet. However, the more you are exposed to this, and don't forget, the Metric Conversion Act of 1973 was the act which was gonna get the US working on metric.
Yeah,
And so, it is just going gangbusters right now. We are, just a couple of decades afterwards, almost 40 years later, you can see we're almost there.
Well, I mean, England's still using miles per hour for speed limit.
I like your feet and our miles.
I mean, we sell our soda by the liter, so.
Yeah, we sell our soda by liters.
Official documents or ban the use of feet?
I think it's the thing that finally, when you buy soda, the 12-ounce soda, it says 0.334 liters, it's the thing that forced that to be on there, or 335. That one? May I borrow your pen for a second?
Anyways.
0.355, or 355 milliliters.
Yes.
Wow, and they actually abbreviated milliliters correctly.
Where it's like,
Little N, big L.
yeah. And that and only like 3 countries in the entire world use imperial, and 2 of them are definitely not together.
You got US, Brunei, and Bahrain, or.
Yeah, and at one point, one of them did, like, their central government was state anarchy.
All right, we're about to amend this. Any questions on this before we adjust it slightly?
So Sonic was driving one of those loop-de-loops we saw in some video games.
Huh?
What are you talking about?
I saw a video on it, that's all.
And I think they take this stuff into account in the background,
In the background of what?
in video games.
I don't play
Yeah,
video games.
Good
so-
video
It's
game
weird that they,
companies do.
it's weird that they don't actually use true values of gravity and stuff like that.
Well,
They usually don't.
Except you assume that they're always taking place on Earth, this fantasy world is on Earth.
Well, they never, if something is meant to be taking place on Earth, they don't always, most of the time they don't even use the real
If it was completely
gravitational.
realistic, it wouldn't be possible.
All right, so let's adjust the problem slightly. We now know for Earth an ideal speed to take this curve. Now suppose he's going at 30 meters per second. What's going to happen to the car?
It's going to slide up and off the ramp.
So if there's friction involved, which way would friction be acting?
Well, the car's going that way. What are you talking about?
The car, if he's going above that ideal speed over there, he would be slowly drifting to the outside of the curve.
Yeah, I was getting there.
And
Okay.
And if there was friction involved, it would be down the ramp.
Okay. Yeah, that way. So friction would be acting down the ramp.
Yeah.
If the speed instead of 30 meters per second or 20 meters per second,
No. He's falling the friction back up the ramp.
and so we have, so that would cause the friction to flip around the other direction. So for the sake of this, let's throw friction into it. And now I believe the coefficient of static friction, because you don't want it sliding, the coefficient of static friction between rubber and asphalt is 0.7. I think that's right.
Wouldn't that, if they were hard bodies, which rubber kind of
We're assuming
rigid, yeah.
vulcanized rubber, we're doing tires, not rubber tree rubber.
Yeah.
And the question is, what is the maximum speed where he will not slip? where a car won't slide.
0.7 for dry roads.
Okay.
0.4 for wet.
After this, we'll calculate for when after it rains.
0.4.
So as established before, if we're looking at a maximum speed, that means he will be traveling faster than the ideal. And so he should be sliding up the ramp, and therefore friction is acting down the ramp. Actually, let me put the friction down on this one right here, and then we'll put the components on this one up here. So the friction is acting to the left and down, to the left and down. Now we have to figure out which one is sine theta and which one's cosine theta.
Well, I don't know, I'd just use what you had, right? But I guess you're gonna have to change it, otherwise, right?
Well, we do have a clue. We could go through and do the vector stuff that we did before, or we could just exploit the idea that the friction and the normal force are perpendicular to each other.
Yes.
Yeah, so yeah, because it's
therefore-
going down and normal force is up. Yeah.
In terms of trig function, that's what we're going for here. This is going to be either f sine or f cosine.
I don't know, you have to explain why you picked that, whatever you picked. So I don't know what you're talking about.
Let's see, that is going to change slightly. All right, so let's break it up then. We have friction acting down the ramp in that direction. This angle here is theta. I'm trying to figure out how much of this force is down and how much of this force is to the left. If this is F here, and there's theta,
Oh, so you have sine going down and cosine going to the left.
Just think of it.
when dealing with perpendicular vectors, if you're breaking them up in the same axes, then the trig function flips. Since cosine was vertical, sine for normal force, sine is going to be the vertical for the friction. So this is F sine theta. We had sine going to the left, so for friction, since it's perpendicular, it will be cosine. That'll save a little bit of the thought process for other things.
Oh, yes, you do. I think I get it. So I guess you always want the F on the backside of your sine, your cosine. That's how you picture things, because I see, like before, how you picked it. So sine opposite over hypotenuse, so you put the F on the backside of the sine, right? And then same on the cosine.
Oh, why it's F sine?
Yeah.
Yeah.
Okay, that's how you determine though that was sine, because if you try to use cosine for your sine, it wouldn't work. You wouldn't have F on the backside, so that's how you picked it, right? Because that's where I always mess up. It's which one to pick. That's what I was asking.
It's always going to be the hypotenuse times the sine or hypotenuse times the cosine for the components.
Yeah.
So that's why it's going to be F times something.
Yeah. I get
My
it.
principal argument is the fact that for perpendicular vectors, when it breaks into components, the trig function will switch. That's what I was going for earlier.
Oh, okay. Yeah. It's the opposite direction.
All right, equations of motion.
Well, we have our original y sine theta. Oh yeah, and our I have her. We have y sine theta. No.
B minus the F.
Oh, it's sine theta. It's mine.
Yeah, B minus F cosine theta, right?
Which way is F cosine theta?
Plus.
It's going the same direction.
Why is it plus?
It's going the same direction.
Oh, okay, yeah, it's going that way.
Yeah.
Okay. Yeah, I see now.
The equations are based upon the diagram here. And the other equation?
Y cosine theta F sine.
Somebody's going to have to talk louder.
Y cosine theta minus F sine theta minus
Okay, I see now. Wait, one quick question. Why would it be plus W? Because that's going the same way as sine theta.
It is, we could have written it as negative and then put a plus sign.
Oh, okay, I see.
Like that, or just distribute the minus sign.
Okay.
All right, substitution. For what do we have a formula? An independent formula.
We've got W and we've got A.
And we have friction, so.
Now, static friction is always enough to keep it from sliding until you hit that breaking point. But since I'm looking for a maximum speed here, we are looking at the maximum static. So I can just go ahead and, so this is S max. So I'm left with y sine theta plus mu s y cosine theta is equal to m v squared over r. And then I have y cosine theta minus mu s y sine theta is equal to mg. Go ahead and bring that over. Again, we have two unknowns. We have y and we have v. Pardon? Okay. I'm going to do one thing first before I divide. I mean, if you see it already, you can go ahead and just do the division, but I'm going to factor y out. So I have y times sine theta plus mu s cosine theta equals m v squared over r. And then factoring y out of the bottom, cosine theta minus mu s sine theta equals mg. And now, as Justina said, just divide them. Okay, divide the left sides, divide the right sides. Y's will cancel out, which is convenient. Since I can't raise the board. So I'm left with sine theta plus mu s cosine theta over cosine theta minus mu s sine theta equals v squared over gr. Notice that if the coefficient of static friction is 0, then we are reduced back to the problem that we just did. So this gives us some confidence that we've done something right. So v is the square root of gr times sine theta plus mu s cosine theta over cosine theta minus mu s sine